Good afternoon, everybody. My name is Tim Ports. I'm the Vice President of Content and the Executive Editor of Biomass Magazine. I want to welcome everybody today to another installment of the Biomass Magazine webinar series. Very happy to have you all with us today and looking forward to what promises to be a very technically rich and insightful webinar. This webinar today, sponsored by IEP Technologies, has become somewhat of an annual tradition. And I know that everyone out there who has dust in their facility that they have to manage and introduces a risk of fire or explosion is going to be finding this webinar very, very valuable indeed. A couple of housekeeping items before we get on with the webinar. We are recording this webinar, so we get a lot of questions up front about, are we recording this webinar? We are recording this webinar. You will have access to it as a registrant. So no need to worry about that. A couple of other items. If you have a question for a specific presenter or the group at large, please feel free to use the GoToWebinar platform to ask that question. It is very helpful for all of us on the production side if you indicate who the question is for, and we'll make sure to direct that question to the person that you've indicated. If the question's for everybody or for anyone, just simply say all. And we look forward to getting to as many questions as we possibly can. Again, today's webinar really focuses on a couple of items. Managing dust in your facility and arresting flames and explosions if they do happen to occur, the technologies that are available to biomass producers or operators of biomass facilities with very real dust risks. And also we're going to talk a little bit about the ways that we might mitigate electrostatic discharges and the risks that those bring along with them. So looking forward very much to today's webinar. Again, today's webinar is brought to you by IEP Technologies. Next slide, please. IEP Technologies, the name to trust for industrial explosion protection. IEP Technologies is the worldwide leading provider of industrial explosion protection systems and services. For over 60 years, IEP has provided protection solutions that can suppress, isolate, and vent combustible dust or vapor explosions in process industries. IEP Technologies can support biomass and ethanol operations through our facilities in the United States, Brazil, the United Kingdom, Germany, Switzerland, France, Turkey, and China, designing and servicing systems with a dedicated team of application engineers, regional sales managers, and field engineers. The IEP Technologies process precise protection for every application. IEP Technologies has more worldwide experience protecting a wider range of facilities against explosions than any other company. With well over 15,000 systems installed, we have developed a unique process to ensure the highest level of protection for your facility. The IEP Technologies process includes material testing and engineering site visit, system design, installation, commissioning, and maintenance. IEP Technologies also offers on-site training programs for the proper operation and understanding of your explosion protection system. IEP Technologies is a member of the Herbiger Safety Solutions business segment, which provides comprehensive industrial safety solutions across a wide range of industries. Saving lives through explosion protection and prevention is the role of IEP Technologies, Gale, and Brillick brands at Herbiger. IEP Technologies is the systems and service specialist for the entire range of explosion protection solutions in dust and gas applications. Gale brings decades of experience in mitigating fire and explosion risks from electrostatic spark discharges, and Brillick contributes its technology leadership in advanced venting systems. These brands complement the flameless venting expertise that Herbiger has accumulated over the decades. You can't afford to let an explosion threaten your critical facility. Let us work with you to keep an explosion from impacting your bottom line. Call IEP Technologies today. Thanks again to IEP Technologies for sponsoring today's webinar. I know you're going to love it. If you're with us next week in Minneapolis for the International Biomass Conference and you have additional questions for anybody on today's webinar, someone at booth 221 would be very, very happy to talk with you. Thanks again to IEP. Let's talk just a little bit about who we're going to hear from today. Martin Cloutier will start off our webinar. Martin is from Jensen Hughes. Martin will be followed by Mike O'Brien from Newson Gale. And rounding out our webinar today will be David Grandaw from IEP Technologies. Once again, I want to remind everybody, please submit your questions, and I'll do my best to direct those questions to the professionals most capable of answering them. And any questions that are for everyone on the webinar will be asked at the end so everyone can benefit. Looking forward to the discussion. Martin, I'll hand the webinar over to you. Go ahead, sir. I'm sorry. Before I do that, Martin, let's talk just briefly about the agenda today. My apologies. We're going to talk about principles of combustible dust explosions. We'll talk about primary and secondary explosions. We'll talk about assessing hazards and ignition risks. I'm looking forward to this new content for me, electrostatic ignition risks and control. We're going to talk about explosion protection strategies, and then we'll talk about process vessels at risk. So once again, now I will send the webinar over to Martin Cloutier. Martin, go ahead.
Well, good afternoon, everyone. It's a real pleasure to attend this webinar, so thank you, Tim. I'm going to, in the next 25 minutes, speak about fundamentals of combustible dust, deflagration, and explosion hazards, briefly talk about some of the usual offenders for ignition sources. I'm briefly going to mention some loss examples and trends, incident trends, but more importantly, I'd like to talk about some of the applicable standards and engineering guidelines that are used to help plant operators mitigate dust explosion hazards. I'll spend a good deal of time talking about what's now known throughout the industry as performing a DHA, or a dust hazard analysis. Specifically, I'll talk about material hazard, equipment hazard, and building hazard evaluations. So starting with the basics, we're all familiar with the fire triangle, what's necessary to actually set something on fire. Bear with me here, I'm going to start with some basic things, so, but the technical content will become more advanced very quickly. But with a fire triangle, basically you need oxygen, fuel, and an ignition source. Anyone who's, as a youngster, perhaps played with flour and throwing it into a campfire, you have a perfect example of what a deflagration or a flash fire is. The only difference between deflagration or a flash fire and an explosion is containment. And that could be represented by a dust collector or a building or any partial confinement, actually. That what happens with the deflagration is there's a rapid combustion which causes fast increase in temperature, causes gases to expand, and it's actually the consequences of the rapid expansion of gases that causes the equipment or building to rupture that's called an explosion. Not all dust will propagate a deflagration. The key properties of the material that will determine whether or not you can have a dust explosion is particle size, which has a dominant effect, chemistry of the material, particle size and morphology, or the shape of the material, and moisture content. If you look at the list on this slide of the many ignition sources, safety practitioners will often tell you that the only thing free in process safety is an ignition source. And when you look at this list, some are intuitively you can evaluate that they're more they have higher strengths than others. Hot work is a common ignition source for fires and less so for dust deflagrations. Those are very strong ignition sources, but there's also what we'll be talking about later in this webinar is electrostatic discharge. So those are basically the two extremes of ignition source strength. Later in my presentation, I'll be talking about the material hazards of wood pellet dust and how sensitive they are to ignition. This is an excerpt from NFPA 77. It gives some perspective on the strength, the relative strength of electrostatic discharge and the minimum ignition energies of different types of material. You can see that if you have minimum ignition energies of wood pellets on the order of 1 millijoule or less, then many different types of, most types of electrostatic discharge are actually viable ignition sources for wood pellet dust. These are what you would call the usual suspects in terms of common equipment that where dust deflagration explosions have occurred. The conditions that are required for a dust explosion to occur within the equipment basically is the dust has to be deflagrable or the dust has to be explosible. Furthermore, there has to be enough dust within the equipment that when it's dispersed, it exceeds the minimum explosible concentration of the material. For example, if you have a bucket elevator that transports wood pellets, the wood pellets themselves might are too large to pose a dust deflagration hazard. However, if the pellets are easily broken up over time, there's dust that can accumulate within this equipment. During startup or a process upset condition, dust can become dispersed in the bucket elevator, and if this occurs in the presence of a competent ignition source, then you can have an explosion. Another example is conveying systems. If the material transfer rate, the ratio of the material transfer rate to the airflow rate exceeds the minimum explosible concentration, then you could have an explosion in the conveying system or the ductwork. Dust collectors are a classic example of an ideal way not to prevent an equipment explosion. Basically, the finest material, which is the most explosible, travels through pneumatic conveying system into the dust filters. At the very moment when the dust filters are pulsed to dislodge the fines accumulated on the filters, that will often cause an electrostatic discharge that has accumulated as a result of the material transfer through the system. These are ideal conditions for creating deflagration inside the dust collector. Similarly, hammer mills are used to cause the material to create finer materials and break up the material. What happens sometimes is there's stones or other material, tramp metal, that winds up in the hammer mill, and because of the rotation, sparks will ensue and often cause deflagrations in this kind of equipment. Here is a table that shows relative frequency of of explosions that occur in various types of equipment. This table lists numbers and percentage of dust explosions that have occurred in various process equipment as reported in incident compilations in the US, the UK, and Germany. The listing shows that dust collectors have the highest percentage of explosions in both the US and the UK incidents. Grinders, pulverizers, and other particle size reduction equipment have also been involved in a relatively high percentage of incidents. The US data shown here was obtained from FM Global Loss History from 1985 to 1995 and from Industrial Risk Insurance Loss History from 1975 to 2001. The UK data is from the Health and Safety Executive for the period 1979 to 1988, and the German data is for the period 1965 to 1985. I don't want to spend a lot of time talking about explosion events involving wood pellets and any basic internet search will show you that loss history is replete with deflagrations involving wood pellet dust. But two events worth mentioning now are the Inferno wood pellet explosion that injured one and resulted in 11 OSHA violations for $43,000. And this happened in 2013. Recently, there was a wood pellet conveyor fire in Port Arthur. This incident is under investigation and resulted in extensive damage. Loss trends related to dust explosions. On average, OSHA indicates that annually there's on the order of 5 fatalities and 28 injuries. FM Global has cited approximately 1 major loss per year. The U.S. Chemical Safety Board performed a study on combustible dust hazards and identified 4 losses where the property damage was in excess of $100 million. These loss numbers don't account for business interruption or reputational damage and economic impacts to the community. OSHA violations where inspectors have visited plants and identified that there are unmitigated dust explosion hazards, penalties range typically on the order of $5,000 to $70,000. So as an operator, plant operator manufacturing wood pellets or handling wood pellets, the key question is, okay, we recognize that we have explosion hazards. How can we assure ourselves that we're actually doing what's considered good in engineering practice? How can we be assured that we're protecting our plant and protecting our workers? Well, fortunately, the National Fire Protection Association has produced a series of standards. They're not codes, although the standards are often adopted into code, but they're codes that can be used as examples of what constitutes good engineering practice at facilities. The codes, the NFPA standards are developed as they're consensus-based standards. They're developed by technical committees that are comprised of stakeholders, insurance companies, manufacturers, operators, and also corporations that produce explosion protection equipment, such as IEP. So the figure in this slide shows basically the hierarchy of standards, the NFPA standards. NFPA 652 was created as an umbrella standard to help users navigate the other standards. Those in red are occupancy specific. NFPA 68 and 69 are used as engineering design methodologies for explosion protection systems, such as explosion protection by deflagration and explosion prevention systems. NFPA 77 deals with electrostatic hazards and how to mitigate those. We'll hear more about that. And NFPA 499 deals with basically how to evaluate and assign hazardous area classification with respect to electrical equipment. The standards up at the top, the red ones are occupancy specific. 664 and 61 relate to wood handling and wood processing and agricultural facilities respectively. So these standards, these NFPA standards, have recently made a requirement to retroactively perform dust hazard analyses. So what is a dust DHA or a dust hazard analysis? This is not a new requirement, but the retroactivity of this requirement, the mandatory retroactivity that you see in these NFPA standards, is new in the industry. So a dust hazard analysis has 3 objectives. One is to first identify dust deflagration hazards throughout the plant and throughout the process. The second objective is to evaluate existing safety measures against good engineering practice as exemplified in the NFPA standards. The third objective of a DHA is to offer practicable recommendations to close the gaps between what's considered good engineering practice and what is actually existing at the facility. Prior to, in recent time, the standards have called them DHAs instead of process hazard analyses. One of the reasons for this is PHAs has a special, the term PHA has a special connotation in process safety management, and there are different methodologies that you can use to identify hazards. Two are FMEAs and HAZOPs, which are commonly used in petrochemical, chemical process safety. These standards are not particularly, although they can be used to perform a DHA, they're not particularly well suited. The reason is that these FMEAs or HAZOPs are good for processes that are very complex. When you look at dust handling equipment, equipment that handles wood pellets, these equipment are very industrially common, meaning the book has been written on how to protect a dust collector. You don't need to use a more complicated, more resource-intensive method such as a HAZOP. So in early days with these NFPA standards, some safety practitioners and operators were performing these process hazard analyses in the PSM style. So in order to avoid this confusion, the terminology DHA was coined and is now used pervasively throughout the industry. Basically, a DHA is broken down into three parts. The first is to evaluate the material hazards. I'll talk more about that. Basically identifying which materials are explosible and characterizing them to determine how violent they explode and what their ignition sensitivity is. Then the next part of a DHA is to look at the equipment by identifying equipment where there are deflagration hazards and determining what protection is appropriate for that equipment. Finally, you would evaluate the building hazards by identifying hazardous accumulation of fugitive dust. And we'll talk more about that later in the next few slides. So one of the first steps in a DHA is to characterize the material hazards. You would want to identify material that may be explosible throughout the process. Sometimes you would take samples throughout various points in the process because due to particle size reduction and changes to the actual material, it might be explosible in one part of the process and not in the others. One of the key things that users or operators should understand about these parameters is that they're not fundamental properties. So for example, Pmax and KST are two parameters that are used to characterize how violently a dust will explode. These parameters are used as input to designing explosion protection by deflagration or explosion suppression systems. The parameters MEC, MIE, MIT, and LIT, they all give an indication of how sensitive the material is to ignition. Some safety practitioners, until recently, have used the concept that was created by the U.S. Bureau of Mines for explosion severity and ignition sensitivity. It's important to understand that the U.S. Bureau of Mines has since renounced the use of these parameters. However, you still see them. They're basically for explosion severity is basically the ratio of Pmax, the product of Pmax and the maximum rate of pressurized relative to Pittsburgh coal. The ignition sensitivity is the ratio of the products of the minimum ignition temperature of a dust cloud, the minimum ignition energy, and the minimum explosible concentration over the same products of those parameters for Pittsburgh coal. These parameters were previously used to obviate the need or negate the need for classified electrical equipment. NFPA 499 no longer promotes the use of these indices, so it's important to understand that they shouldn't be used. Here are some typical values for explosion severity and ignition sensitivity for a number of biomass materials: wood dust, forestry waste, and sewage sludge. We have tested material ourselves, hardwood, where KSD values can be as high as 218 bar meters per second, with minimum ignition energies between 10 and 30 millijoules. The key takeaway from this table is that in terms of ignition sensitivity, biomass is absolutely susceptible to ignition by electrostatic discharge. You can also look at some of the other comparison between coal dust and yellow pine dust, bark dust, and pine dust. They all have very low MIEs relative to coal, on the order of 1 magnitude lower. So if we look at the second part of a DHA, and that's basically to examine individual pieces of equipment and consider their operating conditions and the materials as they're handled in this equipment. You want to evaluate the credibility of ignition sources. Is there enough dust in this equipment to pose a deflagration hazard? Can the dust credibly become dispersed in this equipment? Basically, you're trying to determine, are there credible ignition scenarios for this equipment? And furthermore, is there potential for propagation of the deflagration between equipment? An example in the standards are screeners and classifiers. These items are actually very difficult to protect, and NFPA 64 acknowledges that and does not explicitly require explosion protection for this type of equipment. The same thing can be said for way belts. Certain engineering guidelines and standards will support the case that way belts don't tend to have fires or explosions if they're properly designed. The next part of a deflagration hazard assessment, or DHA, is to look at the building hazards. And by far, the dust explosion incidents which have occurred in industry, which account for the majority of fatalities, are where there's hazardous accumulation of fugitive dust throughout the building. That's when dust collectors aren't working and equipment is emitting fugitive dust. Over time, this material can accumulate on upward-facing surfaces, overhead surfaces that might not be readily apparent. If there is a primary explosion, such as a dust collector explosion or a hammer mill, that may cause fugitive dust throughout the building to become dispersed. So there's a dominant effect. And the secondary explosion involving the dust throughout the building can be devastating, not only because it's a much larger explosion, but now it involves the building and it can cause structural collapse of the building. If you walk through a facility and you cannot discern the surface color underneath of a layer of dust, that would be a good trigger to necessitate the need for an evaluation of whether or not that accumulation is hazardous. NFPA 664 indicates that assuming a bulk density of 20 pounds per cubic feet, if you have dust layers on average 1/8 of an inch thick, that will pose a building explosion hazard. That's sufficient to pose a building explosion hazard. So when you walk through a facility, if you can write your name in the dust or you can't discern the surface color underneath, then that is a point where you need to evaluate whether or not there are indeed explosion hazards within the building. So this diagram conceptually depicts the approach towards dust hazard management. It begins with designing equipment to be dust tight, designing building surfaces so that they're not conducive to dust accumulation on the surfaces. For example, designing purlins so that ledges cannot accumulate dust. And then the next layer of protection would be in the prevention side. If dust can't be controlled by equipment, then it's implementing formalized housekeeping practices to monitor hazardous accumulation of fugitive dust, controlling ignition sources through hot work, grounding and bonding, preventing hazardous electrostatic discharge, and also explosion prevention systems, which are beyond the scope of this presentation, but there are many examples of which in NFPA 69. Finally, if the hazardous accumulation, or if you cannot prevent conditions that could result in a dust deflagration, you would like to look at the last layer of protection, which would be deflagration venting, for example, or explosion suppression. Finally, in cases where you cannot rule out the potential explosion in a building, then you would look at providing workers with personal protective equipment. So thank you for your attention, and I look forward to any questions that you might have.
Martin, fantastic presentation. I promised that today's presentation would be full of very rich in data, and your presentation certainly met that high praise. So thank you for your remarks. We'll move on this afternoon to Mike O'Brien. Mike is the head of marketing and sales at Newson Gale. I'm looking forward to Mike's presentation very much. I haven't actually read a lot or heard a lot about electrostatic ignition hazards. Certainly Martin talked about how most electrostatic sparks are enough to light the wood flour associated with wood pellet production. So it's a very real risk, and I'm looking forward to what Mike has to say about electrostatic ignition hazards and how to best mitigate them. Mike, go ahead.
Thanks, Tim. Good afternoon, everybody. Pleasure to be on this call. Don't often get an opportunity to discuss electrostatic hazards with such a broad audience, so looking forward to it today. Just starting out with the presentation itself, and just going to start with the spark. Very often people look at electrostatics as witchcraft, and what I want to do today is just put some kind of basic ground rules in place in relation to the kind of black art that people think it is. When we boil it down and break it down to I guess the final, the common denominator is whether or not a spark gets discharged. Essentially, the story behind the generation of the spark is the fact that if you look at the picture in front of you, the way that spark has been discharged is that if we imagine the spark moving from the left-hand side of the screen to the right-hand side of the screen, that there's an object that it's been discharged from. And the reason a spark has been discharged from that object is because that object has acquired a voltage, and generally speaking, it's through the normal operation of the powder processing operations, the transportation of the solids into various types of equipment, and the relative motion of the solids and powders in the equipment that leads to the generation of electrostatic charge. What we have to ask ourselves and understand is why a situation has developed where that voltage has been allowed to accumulate on the equipment and has led to a situation where there's been a discharge of a spark. Now, the consequences of the spark are obvious in that if there's a fuel in the right concentration, oxygen to or air to fuel ratio, if it's in the right ratio, then obviously you're going to get ignition of the atmosphere in that spark. So essentially, an electrostatic spark is no different to a spark plug in an engine. It has the energy to ignite the fuel, and that's what you see will cause ignition of the combustible dust if it's present in the right concentration. So when we look at the processing and handling and transportation of solids and powders, it's very energetic. A lot of charge is kind of generated during the movement of the solids, and at the atomic level what happens is that as the solids come into contact with the containment system, like the piping, the ducting, hoppers, all this equipment that's made of metal, if it's a resistive material, which is generally regarded as a material that has a resistivity of 10 by 10 to the 10 by 10, 10 by 1 by 10 to the 10 ohm meters, then essentially it has a tendency to strip more conductive objects of electrons. And what NFPA 77 says, it just takes the transfer of one electron in 500,000 atoms to set up the necessary conditions for a static spark to discharge. So essentially what we see is that as the powder or the solid is moving through the system, it's accumulating charge all the time, and it leaves an opposing charge on the equipment. So if the equipment isn't grounded, generally the conductive equipment, which is reflected in the fact that most of the equipment we're talking about is made from metal, that it retains a charge too. So essentially you have a scenario where as the solid moves through the system, it's accumulating a charge, but also it's stripping charge from the equipment it comes into contact with, and it accumulates a charge too. Just putting into context, there was an academic paper that was done in Germany a few years ago, and basically what they identified was sources of ignition in dust explosion incidents, and obviously mechanical sparks is high up there, followed by smoldering nests. But what they also identified was that electrostatic discharges made up 10% of the 426 incidents that they looked at that had occurred between 1965 and 1985. So obviously it's not very easy to find published data on incidents regarding electrostatic, recorded incidents concerning electrostatic discharges. But based on this study, you can see that it's quite significant, and I would assume that some of those incidents would, the causes of ignition would have dropped into the unaccounted category as well. Some data again on the kind of equipment that's involved in dust explosions. Again, the purpose of this slide isn't so much to do with the fact that there's data out there, but what people tend to concern themselves most with is the classic locations where you get explosions, like in the dust collectors in the silos. But very often what gets missed is the other equipment that's portable. So you're talking about, what we're looking at here is fixed plant equipment. So it's generally permanently bonded together, whereas there's other equipment out there like trucks, rail cars, IBCs, flexible intermediate bulk containers, also known as big bags, and people themselves that can be subjected to charge accumulation and generate a voltage too. So it's important that throughout this presentation we cover both aspects in terms of what good grounding practice should look like. So the primary factors behind static discharge, obviously what I've covered in one of the slides previously, is that as the solids and powders are moving through the system, if they're resistive, and obviously that's based on a resistivity value of 10 to the 10 or higher, then they're going to accumulate a charge by stripping the equipment that they come into contact with of their electrons, and they accumulate those electrons. The reality is that it's actually similar to a charging current. So if you think of a classic scenario where we have voltage equals resistance times current, we have a situation where the charged solids and powders, they are the charging current. And obviously they're coming into contact with objects that, like the silos and the conveying system, the ducting, the piping. And if that equipment isn't grounded, if the resistance to ground is high, so this is the R in the equation, then we have a situation where the voltage of that object will increase, and that's the danger. So that when we get an increase in voltage, we see that what we see is a direction of travel that will lead to the object acquiring so much of a voltage that it will exceed the breakdown voltage of the air around it, surrounding it. So generally speaking, you're talking about 3 megavolts per meter, which is similar to 3 kilovolts per millimeter. And once the voltage gets into that range, that's when the dangerous situation is developing. The problem with that is that it's not visible. If you see a guy lighting up a cigarette in a hazardous location, we know that's a bad idea. But the problem with electrostatic hazards is they're not visible. They're not visible to the naked eye. You can't smell it. You can't see it. There's no tangible way of kind of identifying that there's a risk with the process. So generally speaking, in order to tackle this problem, what we've got to do is we've got to put some benchmarks in terms of our grounding and bonding practices. So we're going to target R in that equation. So we're talking about voltage equals resistance times current. It's very hard to control the current because electrostatic charging of powders and solids is highly unpredictable. But what we can predict and what we can control is the resistance of the equipment that the material comes into contact with. So again, examples of what I'm talking about that kind of rest outside the domain of the the plant equipment that is permanently bonded and should be permanently bonded and connected down to a valid ground is the trucks, it's the big bags, it's the conveying of powders and solids through hoses, flexible hoses, ducting, and also what we can't forget is people. People in their own right, if they're not grounded, they can generate voltages up to about 20,000 volts themselves just through their own movement, which leads to a situation where they can discharge static sparks with energies in excess of 30 millijoules. So the grounding of people along with all the other types of equipment that the material is coming into contact with is essential in a hazardous location. And what you can see is with dry wood, in comparison with other types of materials, is that the MIE can be anywhere between 10 and 30 millijoules, with the resistivity 1 by 10 to the 11 ohm meters when it's dry. So as it's working its way through the system, whether it's being loaded into a truck or offloaded from a truck, or it's going into it's fragmented down to a dust level and it's going into a dust collector. It's got all the right characteristics of being susceptible to an ignition caused by an electrostatic discharge. And again, to put it into context, it's something that we need to control in terms of what type of equipment the pellets are coming into contact with. So to get onto the meat of what we need to address, basically, good grounding and bonding practice essentially starts with the mass of the earth, okay? So what I'm talking about here is that we want to connect any object above ground capable of coming into contact with charged solids and powders, of being able to dissipate that charge down to the general mass of the earth, okay? And the best guidance that we can follow is NFPA 70, Article 250 of NFPA 70, which addresses good electrical grounding practice, which is essentially ensuring that there's no isolated plant equipment above ground that can accumulate hazardous levels of charge. The objective of NFPA 70, Article 250 is grounding from an electrical protection point of view, but it is generally accepted, and it's stated in NFPA 77, that from an electrostatic grounding perspective, we can tap into those grounding circuits and use them to ground the equipment. So if that's permanently installed equipment, like the silos, or if it's portable equipment, like trucks, then we should be finding a way of connecting those particular items of equipment to ground. Now, what NFPA 70 says is that a single rod buried in the ground should be capable of achieving 25 ohms or less. So when you consider that a plant will have multiple rods going in the ground, they might even use the building structure as a means of grounding the building and grounding all the circuits that are in there. The building will achieve a much lower resistance anyway, and any of the kind of plant equipment is capable of doing that too. So generally speaking, what we want is to tap into those circuits, those electrical grounding circuits, to dissipate the electrostatic charge from the equipment, both portable equipment and fixed plant equipment. In relation to electrostatic grounding practice itself, you can see there's a lot of codes of practice that are out there. Generally reflects the seriousness with which professional bodies take the risk of electrostatic discharges, and the one I'm going to focus on today is the National Fire Protection Association NFPA 77 Recommended Practice on Static Electricity. It's a very good document in terms of addressing all sorts of processes and putting in good benchmarks in relation to A, identifying what processes are at risk of static charge accumulation and discharges, and B, what kind of preventive measures can be implemented to ensure we don't get a build-up of electrostatic charges on the equipment or people. So in terms of the industrial scenarios, just make one comment about NFPA 77, in fact. Very often with guidance documents like NFPA 77, you're looking for a common thread, a common way of doing things. And in relation to the grounding of any equipment that's made from metal, so it can be a truck, everything from a truck right through to ducting, through to the silos, micronizers, whatever it is that's made of metal, we should be trying to benchmark a resistance of 10 ohms or less between the object at risk of charge accumulation and a verified grounding point on the plant. So that means then that when we benchmark ourselves against 10 ohms, we know that the grounding circuit that's performing the safety function of ensuring electrostatic charge doesn't build up is more than capable of dissipating the charge to ground. If we see resistance is higher than 10 ohms in the overall circuit, then we know there's an issue with the continuity of the overall grounding circuit, and it must be inspected. The only difference between the grounding of metal objects typically drops into the grounding of people and the grounding of flexible intermediate bulk containers. So there's different benchmarks set against that. For people, they should ideally be wearing static dissipative shoes, so they shouldn't have a resistance down to ground of less or over 100 megohms. There's some standards out there that recommend 1,000 megohms. It just depends on what standard you're going to follow. But generally speaking, the recommendation is 100 megohms. And then when you look at static dissipative flexible intermediate bulk containers like Type C FIBC, the recommended maximum resistance through the bag, as far as NFPA 77 is concerned, is 10 megohms. So they're the only kind of areas where you're talking about materials like shoes, like static dissipative threads in big bags that aren't made from metal. So therefore, there's higher levels of resistance accepted through those. But essentially, what you're trying to do in the case of people is ensure that the shoes can dissipate charge off them based on their own movement. Worst case scenario, if the shoes can't guarantee adequate grounding, then you look at options like wrist straps. In relation to big bags, again, it's very straightforward. You ground the bag against a benchmark of 10 megohms. So typical industrial scenarios. In terms of trying to apply layers of protection, there's lots of different ways this can be done. Lots of people draw their own conclusions in terms of how they want to address the risk. What I would say is, starting at the very bottom, let's say, for example, call it layer 1, is you want to be using FM approved grounding clamps. These are kind of passive grounding systems where typically a lot of people would just use Mueller clips, alligator clips, and while that's fine for charging up the battery on your car, it's not good enough for an industrial setting in relation to mitigating the risks of electrostatic discharges, because very often you're trying to connect equipment like IBCs, drums, trucks. You're trying to penetrate paint coatings that actually provide a very effective insulating layer of resistance between the metal of the container as compared with the insulating properties of the coating that's around it, or it could be covered in rust. Just all these kind of coatings, whatever. But the idea is that by specifying an FM approved clamp, you are specifying a product that has been benchmarked for its electrical resistance, its ability to resist vibration, pull resistance testing, and clamp pressure testing, so that there's a lot of benchmarks in there designed specifically for static grounding protection rationales that are inherent in the testing of those clamps. Moving up another layer, you can have good connections to plant equipment that are kind of permanently in place, like ducting, for example, and continuously monitor their connection back down to a verified ground. That would be layer 2. Layer 3 is an important step because very often the interaction with the equipment is done through an operator, and the common denominator, it really does depend on whether the operator understands the risk and can engage with the equipment that's there, that's been designed to protect him or her the colleagues and the plant itself. And very often when you go from, you know, a passive kind of grounding clamp up to a monitoring system, it's good for them to have some kind of visual reference themselves, because it's pretty much the only thing that they can see. They can't see charge accumulation, they can't see a circuit doing its monitoring of electrical continuity through piping or whatever needs monitoring itself. But when they're given a visual reference, like they're hooking up to a truck or they're hooking up to a rail car, it could be an IBC, that visual reference turns bad habits into good habits, so that they're always looking for something that they should be, you know, referencing themselves, i.e. a green light, which is a good to go signal, so that if they've got some reference, you can turn a kind of a lack of understanding, a kind of a lazy approach to static grounding protection, or maybe it's just forgetfulness, into something that becomes habit, it becomes routine, because it needs, they just get used to using that, you know, visual reference of having a green light to give them basically permission to go. Moving up another layer, you can have that visual indication. Let's say you're grounding a truck, but you might want to interlock dry contacts with the process, so that if grounding is lost during the process, then you've got the option of interfacing the dry contacts with electromechanical devices that can stop the flow of the biomass material into or out of a truck or any other piece of equipment that you might be using. So it gives you an added layer of protection, so that if grounding is lost, for example, if the operator can't eyeball the ground status indicators for the entire operation and they have to do something else, then at least you've got the fallback position, so that if grounding is lost and if the resistance goes above 10 ohms back to the verified ground, then it will shut down the loading process or unloading process. And then moving up another layer, then you can get bespoke type of grounding systems that not only have the visual indication, have the ATEX and FM approved clamps, have the interlocks, but also actually verify a true earth ground. So that's specifically for scenarios where you might have a truck out in the field, or, you know, delivering biomass material to the plant, or you might have, you know, it could be a situation where the truck is getting loaded up with material from a supplier, and there's no grounding in place that would satisfy the safety concerns of the company in question. So what they can do is they can specify a grounding system that's mounted on the truck, and I'll just show some examples in a minute of how they can actually verify their own true earth grounds by just connecting up to plant equipment and seeing if it is actually connected to the mass of the earth itself. So here's an example. This is on the top left, this is a static grounding system for trucks, and very often the truck is present at the silo and it's either getting loaded, or maybe it's interfacing with the air entrainment system into the plant, or maybe it's just offloading by gravity. Whatever the situation, when you're loading a truck or unloading a truck, the sheer size of the truck and the sheer quantity of product being transferred means that it's one of the biggest risks in terms of electrostatic hazards. Very, very high voltages, you're talking over 100 kilovolts, can be generated through the transfer of product into or out of trucks. So you're talking very, very high energies, static spark discharge potential. And the reason it's important to look at trucks is because this is usually where dispersion of a dust cloud can happen as well. So you've got the combination of electrostatic charging, very energetic electrostatic charging, with the dispersion of a fuel. And the last thing you want is a spark coming off a truck at those energies. The visual reference is a good one, because if it's a driver in control of that process, or if it's a plant operator, again, it just reinforces this idea: are we good to go? Is the truck grounded? Can I move on to the next process? Can I make those connections, like hose connections or whatever method has been used to load the truck or unload the truck? That visual reference can be the difference between them doing it and not doing it. Obviously, if the grounding system is interlocked with the process, then that mitigates some of the risk of them not grounding, because nothing can happen. In relation to what we've learned over the years, very often operators, drivers can connect up to parts of the truck that are not electrically bonded to the tank and the chassis of the truck. So in this example, we've got this kind of strut that's joining two mud guards together. What this product will do is identify if it's connected to the truck's capacitance value relative to worth, and we have a means of identifying a good connection onto the body of the truck, as opposed to other parts of the truck that are isolated from the tank of the truck, because it's actually the tank is the equipment that's going to get accumulate very, very high levels of electrostatic charge and consequently very high levels of voltage. So that clamp needs to be connected onto the chassis of the truck. Another example is where you've got multiple components in a conveying system, a lot of ducting, a lot of piping. Maybe it's broken down on a regular basis for cleaning. You know, stuff gets stuck, it needs maintenance, and those connections are remade. Sometimes those bonding connections aren't put back in place, and they can get missed. So obviously you can look at using a grounding system that can monitor multiple pieces of equipment. I've got a better example on the next slide, where the grounding system has visual indication for the operators, but it can actually monitor 8 different pieces of equipment at the same time. Doesn't necessarily need to be done in this fashion where we're looking at piping and a fluid bed dryer and a portable IBC. But basically it's just using, the technology is designed to monitor all those pieces of equipment independently, ensuring that the resistance of that equipment back to the ground reference is 10 ohms or less. And each of those channels, monitoring channels, has their own relay that can interface again with anything that can raise awareness of a hazard. If there's lost ground, if any of the equipment loses its ground, or if it's hooked up to a PLC, then the PLC can indicate that there's a problem with grounding in the hazardous location as well. So just another aspect, another dimension in terms of grounding multiple pieces of equipment, because the last thing you want is to be specifying multiple grounding systems all over the place. This is the type of system that can hit 8 different pieces of equipment at the same time and ensure that they're all monitored to 10 ohms or less. Again, just another example, if you're loading, for example, rail cars, and you want to ensure that the piping leading into the rail car is got grounding, you can monitor multiple components in that scenario as well. Back trucks, widely used. Biomass facilities definitely come in to clean up any of the excess dust that's falling around the place. Very extensive use, dry, particularly both wet vac and dry vac applications. But again, the power of these things, they generate immense levels of electrostatic charge, and consequently the truck itself can carry a massive voltage if it's not grounded. So if the truck is coming onto the facility and it's moving around the place, because they're so portable and so flexible in their use, it's very difficult to find dedicated grounding systems at the client side to actually provide any grounding protection. So essentially we reversed it, so we put the grounding system on the truck. So when the truck goes around the plant, it can connect up to metal equipment like in this picture and assess whether or not the equipment like the tank in the picture has a connection down to earth. So effectively grounding the truck through its own grounding system with the visual indication, again reinforcing the idea that obviously what we want to do is we want to target the operators and make sure that they fully understand that they've got to ground stuff before they do anything, supplemented by an added layer of protection with interlock controls. That's just one example of, again, going with the visual reference. The ground status indicators go green, informs the guy doing the operation that he's good to go in terms of starting the vac operation or whatever the next stage in the process might happen to be. But always the rule of thumb and the principle always is in relation to any process at risk of electrostatic discharge is grounded and bonded first before anything is done. So again, this green light philosophy reinforces the idea of step 1, grounded, step 2, move on to the next thing. And the grounding clamp is always the last operation in the overall transfer operation or loading operation, whatever it happens to be. So that, ground it first, do the operation, the last operation, take the clamp off and return it to the system or return it to a storage point. Hoses, again, they represent the risk whether they're used inside the plant or if they're used in a mobile setting like a truck. They should be tested regularly because they are subject to a lot of mechanical pressures, and it can be very, they can be treated very, basically they operate in a very tough regime, And the helixes that are present within, you generally tend to have a metal helix that joins the couplings. So that acts like a mechanical kind of rib to keep the hose open, but has a secondary function in terms of ensuring that the couplings and the hose itself never builds up a charge. Because if you've got the movement of the solids through the hose, it can easily, the couplings can get enough charge to discharge a spark. So what you want is a portable. This is just an example where coupling, the internal helix has dislodged itself through just repeated use, and that coupling itself is in fact isolated, and the capacitance of that coupling has more than enough of a surface area to hold on to a charge that would lead to a voltage that with a spark and with enough ignition energy to light a combustible dust or ignite a combustible dust. So essentially what you want, again, when it comes to the operator,
Looks like we're having some technical difficulties. Bob, can you hear me?
Yes, sir, I can hear you fine.
All right. Well, that was Mike's last slide. Maybe if we can get Mike back, we can loop back in with his presentation. With an eye on the time and with an eye on keeping the show moving forward, we're going to go ahead and ask Dave. A little bit accelerated timetable here, Dave. Show business, right? But looking forward to how you're going to bring all this together. That was a fantastic presentation by Mike. A lot of interesting stuff about electrostatic sparks, and maybe we can wrap that last slide up when we go to a Q&A session and just have Mike talk about what we're going to talk about relative to all that in the Q&A. But for now, let's keep the show going and keep the webinar on track and move forward with Dave Grandaw from IEP Technologies, today's sponsor. Dave, go ahead.
Okay, good afternoon, everyone. This last section, we're going to talk about how do we address the abnormal or the unusual condition that can occur at a biomass facility in which an explosion can initiate and propagate. Doing a proper DHA, having proper housekeeping, good dust collection, good control of ignition sources are all critical parts of a protection philosophy to minimize the risk that an explosion can occur within a facility during normal operating conditions. Unfortunately, abnormal conditions occur, and those conditions, whether it be a breakdown of equipment, whether it be something that a mistake made by an operator, any things like that can lead to conditions where a deflagration may occur within a vessel, and subsequently when a deflagration occurs within a vessel and that vessel ruptures open due to the pressures from the explosion, if the housekeeping is inadequate, when that flame is ejected, it will cause a secondary explosion, and that's the one that really is the devastating one that can destroy the facility. Because of this, NFPA has a number of different standards that Martin had covered earlier. The one probably most specific for a biomass facility would include NFPA 654, which is the processing, handling of combustible particulate solids. NFPA 664, which is for wood processing, and then the fundamentals of combustible dust, NFPA 652, which is a relatively new standard in which all of the other industry-specific standards are striving to meet those minimum prescriptive requirements. Now, these standards basically tell you where explosion prevention techniques are needed. There's a couple of standards that then tell you if you employ explosion protection measures, how must these measures be designed? And that would be NFPA 68, which covers deflagration, venting, and NFPA 69, which covers explosion prevention systems. Included in explosion prevention systems are items such as spark detection, isolation, suppression, containment, and inerting. Now, containment and inerting are two of the primary explosion protection means that can be used in industry in general, not very commonly used in biomass facilities, however. Containment is building the vessel strong enough so that it can handle the pressures from a deflagration. So building a vessel strong enough to handle that 100 to 150 psi pressure that could be generated. Inerting is a method in which you're running in an oxygen-depleted atmosphere. So you're running in an oxygen-depleted atmosphere below the minimum oxygen concentration necessary for combustion of that particular material. This is very seldom done in a biomass type facility because the air that's basically moving material through the process is being exhausted to the outside. It's not being recirculated back around in a closed loop type system. So to put a nitrogen or a CO2 blanket on inside these vessels would mean that you're dumping a lot of nitrogen and CO2 to the atmosphere. It becomes a very expensive explosion protection methodology. By far and away, the most common method for managing explosions at a biomass facility would be explosion venting. An explosion vent is an opening in a piece of process equipment or building through which combustion-generated gases can flow and then expand to the outside. The whole purpose for an explosion vent is to keep the pressures from this deflagration at or below that which would cause rupture or even deformation to the vessel or the building that the explosion vents are positioned on. Now, explosion vents come in a lot of different styles. The styles that we are showing here in this slide are rupture style vents. So these are basically vent panels that are pre-scored or pre-cut at certain intervals with small tabs of metal in between. When the pressure, the opening pressure of the vent has been reached, then this vent panel tears open, if you will, on three sides. The other side acts as a hinge, opening up to relieve that pressure to the outside. There are other types of explosion vents that are available. Some are vents similar to this, but they're held on with plastic bolts. There are some types that are held on with magnetic latches or spring-loaded latches. There are even gravity type bolts, vents that are out there. In almost all cases, whatever style of explosion vent that's being used can come with some sort of a burst indicator, so that if you have an explosion and this vent is called on to open and to relieve the pressure, you can get a signal back at your PLC, to your alarm system of some sort saying that we had an event, probably was an explosion, better shut the process down. So since explosion vents are passive devices, generally lower cost devices than other types of explosion protection technologies, they're certainly preferred. So when can we use explosion vents? The first thing you have to ask at a biomass facility when you're looking at explosion vents is, can I throw that fireball in a safe area? Is there a place that we can relieve this fireball so that when it ejects, we're not putting people at harm's way, we're not directing it at a building or at a parking lot or at a sidewalk or something along those lines, because you will get a substantial fireball that is that's released from a vented explosion. That fireball can be 7 to 8 times the volume of the vessel, and it can eject for more than 50 feet. So it's very, very critical that when evaluating the possible use of explosion vents, can we send this to a safe area? If you can locate explosion vent to an area where free of personnel, free of areas that could start secondary fires, then venting certainly should be considered. This particular graph, we'll see two different curves on this graph. The top one would just simply show a deflagration or explosion that occurs in an unvented vessel. What we're trying to do is keep that pressure below the strength of the vessel. In fact, NFPA 68 recommends no more than 2/3 of the rupture pressure of that vessel. A couple of things I'd like everyone to take away from this graph. You have an opening pressure on an explosion vent that's called P stat, or the static pressure in which that vent is going to open. that P stat is not the ultimate pressure that you're going to see during this vent to deflagration. It does take a finite amount of time from the time that the explosion vent opens to the time that you get the full effects of that vent opening, and you reach the peak pressure during this incident. That peak pressure is called the P-red, or the reduced pressure after venting. So it does take a finite amount of time, and the point of this is if you have an explosion vent that's designed to open up at 1.5 psi, and your vessel is only strong enough to handle 1.5 to 2 psi, you probably are underprotected, because it does take time for that vent to fully open and you get the full effects of that vent. NFPA 68 is used for sizing of explosion vents here in North America. And one of the interesting things about NFPA 68 is it does allow for the venting of inside vessels. If you have a vessel that's near an outside wall, you can put the explosion vent on it, duct it to the outside, and then eject that flame to the outside. The length of the duct will have a huge consequence on the amount of vent area, or penalize you in the amount of P-red that you should expect to see in your vessel. However, it's very important to understand that duct length, any bends or elbows, and any enclosures over the ends of the vent, any vent cap, if you will, if you're going straight up through the roof and you're putting some sort of a cap on it so you don't get rain and the environment into that vent duct, those all will impact the efficiency of that venting solution. So it's really important that if it's inside vessel, consider putting vents with a duct on it if you're right near an outside wall. But what you don't want to do is this. The picture we see here is an explosion vent with plastic bolts inside a vessel, inside a building, with no vent ducting on it at all. Because basically what you have is you've created a weakened part of that structure, in which the first thing that will blow off would be this vent panel, but you'll be blowing this fireball directly into the building, stirring up dust from the pressure. Pressure exceeds the flame during a deflagration. That pressure stirs up the dust, the flame comes along, ignites the room, and then you have the secondary explosion. So it's very, very important. Do not put explosion vents on an inside vessel if it's not ducted properly to the outside. Now there are a means of putting on venting for inside vessels that do not have to be directed to the outside. These are called flameless explosion vents. And basically what a flameless explosion vent is a device in which you have either a rupture panel or a spring-loaded plate, if you will, that due to the pressures from the explosion will open up, and then the hot gases and flame will go to a metal mesh. The metal mesh acts as a heat sink to absorb the heat, so that the flame is essentially absorbed in that heat sink, and this is what that heat sink looks like. And then all that then is ejected would be hot gases and vapors. There is some relatively high temperatures that are ejected from these, so you do have to have a safe zone around the perimeter of flameless vents. But flameless vents are often a good alternative to standard venting especially for smaller volume applications. The next style of explosion mitigation would be explosion suppression systems. Explosion suppression system is a system that detects an explosion in its incipient stage before the pressure rate gets so high that that can't be controlled. It detects this using either pressure or radiant energy detection, and then very, very quickly suppresses the explosion prior to any sort of rupture or damage of the vessel. Works on the principle that during an explosion you have a pressure wave that's traveling at the speed of sound. At the same time you have a flame that's traveling somewhere between 2 to 10 meters per second. So you detect that pressure while the fireball is very small, and then quickly inject some type of a suppressant to put out that deflagration. In this example we see explosion occurring within a vessel. Pressure has been detected by the pressure sensor. The agent, which is a sodium bicarbonate based agent, quickly puts out that explosion, and the pressure is quickly mitigated. Explosion suppression systems are very similar to fire suppression systems, in which you have three main components. You have detection, control, and extinguishers. Mentioned before that detection is typically pressure type detectors. There's two styles of pressure detectors. There are threshold type detectors or stack detectors that are looking for a certain set pressure level. There are also rate of pressure rise detectors. And rate of pressure rise detectors are actually not looking so much for a fixed set level, but looking for a rate of pressure development that would be synonymous with an explosion within a type of a vessel for a specific type of hazard. The value of the stack type detector, which is what we're showing on this leftmost box, would be to help minimize the chance of any false actuations due to process pressure imbalances. The control units are devices that monitor the detection and initiate the activation of the explosion suppression vessel. One of the important roles of the control panel is to interlock with any equipment that moves product or air through the protected volume, so that should a deflagration occur, you're shutting down the process. You stop feeding fuel to the vessel that's been affected by this incident, and you stop sending possible burnt material out of this vessel to other parts of the plant where another explosion can occur. The extinguishers are typically use a dry chemical suppressant, and the way the suppressant actually puts out a deflagration is the suppressant, when the agent front meets the flame front, the agent acts as a thermal barrier, or absorbs the heat from the flame front, dropping the temperature below the minimum ignition temperature necessary for that fuel. In other words, we've got to get the agent front to the flame front very, very fast. So you have to see very, very high agent velocities, such as we saw in this video, in order to get that agent front into that vessel to wherever that fireball is and to arrest it within milliseconds. Typical explosion suppression system will detect, discharge, and have put out that deflagration in less than 100 milliseconds. It takes 120 milliseconds to blink your eye, so literally less the time it takes you to blink your eye. This incident will have been initiated and controlled by an explosion suppression system. And it has to be that fast, because if it takes much longer than that, then the rate of pressure increase during a deflagration will get so high that it can no longer be controlled, and you'll have a ruptured vessel. Some of the things that are taken into account when an explosion suppression system is designed is the explosivity characteristics of the fuel, what type of operating conditions, whether it be operating temperatures, operating pressure, that can occur within the protected vessel, and how strong is the vessel, what's the vessel geometry, what's its volume, and so forth. Computer modeling is typically done to assess an explosion protection system to determine whether or not the explosion suppression system is going to be adequate for that particular application. There's quite a number of different factors that will be looked at when you're evaluating the efficacy of an explosion suppression system and the resulting reduced pressure after suppression. Regardless of whether explosion venting or explosion suppression is being used on a vessel, it's difficult to predict exactly where inside that vessel this explosion may start. If it starts somewhere near the mouth of the vessel during a suppression system, or really if it starts anywhere within the vessel during a vented system, you have the threat of protecting the vessel but having that flame propagate to other areas of the plant that may be unprotected. And if that were to happen, then you run the risk of having a secondary explosion. You protected your primary vessel. In a case like this, it would be the dust collector, but you protected that vessel while that fireball is left unchecked to wherever you're picking up the dust from. As a result, NFPA has some very specific requirements. You must mitigate any flame propagation from one vessel to another. And that can be done using either an active method or a passive method. Excuse me. And an active method of explosion isolation could be the use of dry chemical type suppressors, or it could be the use of high-speed isolation valves. And this next slide shows examples. Here's a dry chemical extinguisher that would be used to create a chemical barrier within that duct. So should an explosion occur within the vessel where this duct is connected to, this extinguisher would be called on to put out a deflagration. High-speed isolation valves can also be used, but quite frankly, in the biomass industry, they're not very cost-effective, so it would be seldom that you'd see this style of valve used for your industry. An increasingly common means for mitigating flame propagation in the biomass industry, especially on the inlets of dust collectors, would be what are called passive isolation valves. These passive isolation valves work on the principle that there's the pressure traveling faster than the flame. So what the pressure traveling through the duct will do will actually cause the valve itself to to close. So here's an animation of a flap style isolation valve. And we'll run this a little bit slower motion. So we have the normal airflow, the dust-laden air traveling to the dust collector. When the deflagration occurs, the pressure precedes the explosion, causes the flap to close, and creates a mechanical barrier. So when the flame gets there, it's stopped. So this is one of the more common types of passive isolation protection that are on the market. Just some of the factors that can influence what type of protection methodology would be used. Certainly the location of the vessel and can that vessel be safely vented would be a big factor. The inlet duct configuration, that'll tell us whether or not a passive isolation valve is feasible for that application. The exhaust duct, say on a dust collector, is it going to the outside or is it going back into the facility? There's some NFPA requirements that say if that duct is, that air is exhausted back into the facility, you need to have isolation on that duct. Operating pressures will have an impact. Inline fans, which are potential ignition sources, certainly will have an impact on the type of protection being used. And certainly the explosivity characteristics of the material being handled. There are testing methods that are used to determine some of those factors which Martin had covered earlier in the presentation. This is an example of a type of a vessel used for determining KST values, for instance. And some of the different testing methods that can be used for understanding the characteristics of the material. This also was covered a little bit earlier by Martin, but these are some very common tests that are used for materials that might be found in the biomass industry. This last section, we're just going to quickly go through some of the types of vessels that we see the most common risk of an explosion at the facilities that you may be working at. And certainly the one that probably has the highest probability for an explosion would be a dust collector. Dust collector, air material separator, filter receiver, bag house, all these separate dust from the airstream, usually with some sort of a filter media inside. And these provide the main threat for an explosion in a plant because the finest dust in the entire facility is found in these facilities, and that's bad for a couple of reasons. The finer the dust, the easier it is to ignite. So think of it as kindling versus a log. Easier to ignite kindling than it is a log. It's the same with dust. Also, just like kindling versus a log, once it's ignited, there's more surface area per liter of material, if you will, for heat absorption. So it's going to burn faster. So you're going to find the highest explosivity properties in dust collectors versus other types of vessels within the facility. One other big danger with dust collectors is oftentimes dust collectors are used to service different areas of the facility. So a dust collector may be picking up from a sander. It could be picking up from a grinder. It could be picking up dust off of a belt or a drag conveyor, all going back to the same dust collector. So if you have an explosion within that dust collector, multiple areas of the plant could be affected by any propagating explosion. So these certainly are areas of great concern when you're looking at mitigating the risk of explosion within a facility. Cyclones, another type of air material separator, somewhat the same threat as what we see with a dust collector. It just separates air, dust from the airstream a little bit different than a dust collector, but really the threats are very, very similar. Mills, grinders, pulverizers, very active ignition threats within a biomass facility, especially if that material is dry. Material conveying, whether it be pneumatic conveying or mechanical conveying. And an example of, here's an example of an explosion that occurred at a facility that had storage vessels, whether it be hoppers, silos, or bins, where an explosion propagated from one to the next to the next. It's interesting in that storage vessels in and of themselves don't seem to have inherent ignition threats. But if you think of all the other vessels within the facility, what happens to that material once it's been processed? It ends up in a hopper or a bin or a silo. So an ignition source generated in one vessel, it might not find the right dust-air mix until it's dropped into a vessel, and then the explosion can occur. Bucket elevators are another example of vessels through which explosions can initiate and propagate. Typically in a bucket elevator, you're really worried about the boot or the bottom part where the material's fed in, and the top part, the head, if you will, because that's where the dust cloud and the ignition source threats are most likely to be found. So to kind of summarize what we've talked about today, when you're looking at the threats that you have in a biomass facility, you really want to do a hazard evaluation. You want to look at what type of normal, abnormal, and upset conditions can occur, and what sort of ignition properties you have of the material that you are handling. You want to then assess ignition control, making sure that during normal operations, you're not going to have electrostatic discharge threats that could cause an explosion. You're going to have the properly classified electrical equipment within the area. That you're going to try and control frictional heating, impact sparks, proper hot work procedures for the operators, good housekeeping and dust collection within the area, good operator hazard awareness and training, so that we minimize the chance that an operator can do something that could initiate an explosion. And then evaluate the explosion risks on specific vessels for explosion protection and any propagation threats that may occur.
Dave, are you finished?
Yeah, I sure am. Thank you.
Oh, yeah. Thanks, Dave. Appreciate that. Well, we're at the bottom of the hour. I do have a couple of questions that I'd like to pose to the group. I do need to keep an eye on the time out of respect for everybody's time, and so I think I'll just pose this one to the group, and we'll see kind of what kind of time we've got left after that. And the question is from Prashant Bajaj, and his question is, how dry does the dust have to be considered a fire hazard? When cleaning, often water is used, but there's still some stuff left behind sticking to the floor and the surface of our facility. How dry does dust have to be considered a fire hazard? And I'll just pose that to the group. Is there an impact on moisture level and sort of the fire hazard or explosibility of that dust?
In general, this is Dave Grandahl. In general, if the moisture content is 30% or less, then you are, especially with a organic dust, then you are in an explosion risk condition.
Anyone else want to add to that?
Not from my end, no.
Mike, we lost you earlier. Is there anything that you'd like to say? We just missed the last slide, and if you'd like to, if there's anything that you feel like is really important to leave folks with relative to that last slide, glad to have you back. Sorry about the technical difficulty.
No worries, Tim. No, I think it was lost on my end. Yeah, again, the point I was making was just to make sure that hoses are tested on a regular basis, because very often they are subjected to, what I would describe as industrial treatment. The metal helixes that basically keep the mechanical strength of the hose in place also have a secondary function to bond the couplings. So if you have a break in continuity through the helix, or the helix loses its contact, its connection to the coupling and any hoses downstream of that coupling will be isolated and will accumulate hazardous levels of electrostatic charge as well. So testing of hoses on a frequent basis is a very good practice to engage in, electrical testing.
Got it. I think this one's probably going to work for the group, and we'll let this be the last question of the day. And this question comes from David McKinney. And I just wonder what people's thoughts are. And David's question is, should facilities be built to the NFPA or FM? Is there a general idea of difference in cost relative to that? So does certifying to these different standards have a different cost? And is there a difference in your guys' mind between NFPA or FM? Go ahead, Martin.
Well, actually, I can speak to that. It's important to recognize that NFPA standards and FM standards have two entirely different risk criteria. FM Global is a property insurer, and those standards are developed admittedly by FM, not with the intention of saving lives, although that is an effect or a consequence. The primary objective of the FM data sheets are to prevent property damage and business interruption. The NFPA standards are consensus-based, so they do represent all of the stakeholders that have who would want to have a say in what protection is required. So if you look at FM, they produce excellent standards, and often there's significant overlap between the two sets of documents. However, the recommendations and the prescriptive requirements that you'll see in the FM standards are based on the risk tolerance of the owners of the insurance company, which are also the operators, and also based on how much the insurance company believes that the insured should be willing to spend. Having said that, again, FM has an excellent set of standards. They do a lot of great research, and often there's cross-fertilization, cross-pollination between the two sets of standards.
I appreciate that, Martin. Anyone else?
Yeah, Dave. Just this is one last point on that. The factory mutual FM individuals are heavily involved in the development of the NFPA standards. So they do have a very strong presence and a lot of input. A lot of FM testing is incorporated into the development of the standards that are put out by NFPA. So there is you do see a lot of commonality between the two.
And if you don't mind, I'll just add one more example. The methodology that FM uses to estimate vent size or to determine vent size requirements is slightly more conservative than the NFPA methodology. However, the origin or the source of the fundamentals on which the correlations in NFPA 68 are based stem from the methodology that was developed by Franco Tamanini at FM Global. There are big differences in vent size requirements when you look at low KST, low PMAX, low RED, PRED applications with FM's proprietary software, DustCalc, but that's mainly the only area, class of dust where you would see major differences between the two. So in summary, the FM methodology for determining vent size is slightly more conservative. They envelope more data than the FM methodology, but they're both very similar. Thank you.
Thank you all. And gentlemen, we're going to have to wrap it up here. I want to thank Dave and IEP Technologies. This is our third year doing this webinar. It's great every year. I think it's a real value for our readers. And so I want to thank IEP Technologies and certainly all three of the speakers today. If you want to see more from IEP Technologies and really from anyone in the biomass industry, I want to invite everybody here to Minneapolis next week for the International Biomass Conference and Expo. It actually starts Monday, but if you're local or you feel like, gosh, the content was so good, there is a ton of content, something like 125 different speakers across 3 days. The tour, unfortunately, on Thursday is sold out, but we have plenty of seats for everybody Monday through Wednesday. Over 170 producers already registered for the event, so there is a $250 discount for anyone that does want to take us up on that. Join us here in Minneapolis. It's supposed to be beautiful up here next week, so certainly welcome anyone to come. Look forward to seeing you. And finally, some upcoming events here. Again, all of the activities next week here in Minneapolis, 3 different pre-conferences, the International Biomass Conference and Expo, and then we're back here in June for the International Fuel Ethanol Workshop and Expo and the National Advanced Biofuels Conference and Expo. My name's Tim Ports. I'm the executive editor of Biomass Magazine. It has been our pleasure hosting you today for some great content. Hope you'll join us again next time on the Biomass Magazine webinar series. Have a great afternoon, everybody. Thank you so much.